1942, live fire test. Order signed, clearance granted, 1 fuse seated. I logged the round, closed the breach and stepped back to inspection distance. 1 detonation came early. The report was sealed that night. 1940, the United Kingdom is on the defensive. The British Expeditionary Force has been evacuated from France, but a large share of its guns, vehicles and sites are not recovered. Planning assumes a possible German landing on the English coast, followed by a rapid movement of armoured vehicles toward ports, rail junctions and airfields. Regular formations retain priority for modern anti-tank guns and standard ammunition. Local defence formations operate with limited stocks and uneven training pipelines. The Home Guard expands quickly. Many units are composed of older personnel and men reserved from regular service. Then their formal task is point defence, delay and denial of key routes until regular forces can respond. Their practical problem is close-range armour. Rifles and light machine guns can suppress infantry. Obstacles and roadblocks can slow a vehicle. A stopping action still requires a weapon that can damage armour at short distance without specialised towing, large crews or complex optics. Existing stopgaps are not reliable solutions at scale. Grenades, petrol incendiaries and improvised mines require proximity and exposed crews. Standard field artillery cannot be issued in sufficient quantity during 1940 and 1941 because production is constrained and the army has overseas requirements. The 2-pounder anti-tank gun is effective but is not available for every coastal platoon and every airfield detachment. And the bureaucratic requirement becomes explicit. Provide an expedient anti-tank capability that can be manufactured outside the main artillery supply chain. A similar emergency logic appears on the Soviet side in 1941 after the German invasion. Soviet forces face armoured thrusts that reach operational rear areas and disrupt depots, repair parks and training establishments. Local defence lines are built with mass-produced tools that are plain in appearance and hazardous in use. Anti-tank rifles, bundled grenades and improvised mines are issued because they can be made quickly with less precision than a modern gun. The institutional demand is comparable to Britain's in 1940. Create a measurable anti-armour capability that can be counted, distributed and used by units operating on shortened training schedules. In Britain, the demand moves through the War Office and the Ordnance Board under unusual political pressure. The constraint is not only design competence. It includes steel allocation, machining capacity, tyres and fittings, fuse manufacture, and a workforce already engaged on aircraft, engines, radios, radar, components, and standard artillery. An expedient weapon is attractive if it can be built by firms outside the established ordnance supply chain. The goal is not refinement. The goal is a deliverable quantity measured in months. One answer proposed for that gap is the Smith gun, formerly described as a 3-inch smoothbore anti-tank piece. The concept is to provide a low-velocity projectile thrower with minimal recoil complexity, produced quickly, then issued to Home Guard units as a last-ditch barrier. And it is not intended to replace standard anti-tank artillery. It is intended to cover a road approach, a hedge line, or an airfield perimeter where engagement distances are measured in tens or a few hundred yards. The design originates with retired Army Major William H. Smith, associated with Trianco Limited, a firm better known for general engineering than for ordnance. The first concept is practical rather than theoretical. It removes the complex elements that slow conventional gun manufacture. It avoids a high-velocity barrel requirement. It reduces machining steps in the carriage. It substitutes a low-pressure ammunition concept for a precision recoil system and a long-trail carriage. Official review is uneasy. Safety and handling are immediate concerns. The users are expected to be volunteers with limited live-fire time. And a weapon that depends on careful drill and reliable fuses risks becoming a liability in that environment. The Ordnance Board is not persuaded by the initial submission. Political attention intervenes. A senior-level demonstration is witnessed, and production is directed despite reservations. That decision reflects the administrative culture of mid-1940. A measurable anti-tank allocation to the Home Guard is treated as a strategic necessity, even when the technical case is incomplete. Production planning begins in 1941. Deliveries do not appear immediately. An expedient design still requires controlled tolerances and consistent metallurgy. Barrels must be bored and finished to a usable, smooth bore. Breech components must align consistently with fixed ammunition. Shields require fabrication and mounting that will not loosen under firing. Wheels must bear load and must not fail under repeated tipping. Tyres and hubs are not free items in a rationed economy. The trailer requires its own axle, couplings and storage fittings. The supply chain adds a second layer of delay. Ammunition must be produced in parallel, and the ammunition is not standard artillery stock. The Smith gun's value depends on projectiles that are safe in storage, safe in loading, and consistent in functioning. Fuse manufacturers already under strain for mortar bombs, grenades, and artillery shells. Small variations in fuse sensitivity and seating can become fatal in a low-velocity weapon that is fired close to the crew and often from improvised positions. By mid-1942, the first batches are delivered, and by the beginning of 1943, roughly 3,000 are recorded as issued to Home Guard units. An initial placement is concentrated in coastal defence areas and around vulnerable airfields in southern and eastern England, where likely vehicle approaches can be channelled. Some are also distributed to regular forces assigned to static defence, including airfield guarding units. This allocation follows a bureaucratic logic. Fixed sites can prepare level pads, guns can be stored under cover. Mobility demands are limited to short moves along perimeter tracks and between prepared positions. The physical scale is disproportionate to its intended simplicity. Common technical descriptions place the weight around 604 pounds. Barrel length is approximately 54 inches. Nominal caliber is 3 inches, with the bore often specified slightly over 3.18 inches. Crew requirement is typically 4. The crew size is not driven by mechanism complexity, and it is driven by the labour needed to move the assembly and to control its unusual firing posture. The defining design feature is the carriage concept. In travelling configuration, the gun lies on its side between its wheels. In firing configuration, the crew tips the entire assembly onto one wheel. That wheel acts as a base plate and turntable. The second wheel becomes an overhead shield element and partial cover. The result is a weapon that can traverse through a full circle without a conventional trail. That feature is mechanically simple. It is also unstable unless the base wheel is seated correctly and the ground is firm and level. This configuration is a manufacturing shortcut. A conventional field gun carriage requires a trail, spades, and a recoil system that keeps the barrel aligned. That the Smith gun substitutes geometry and mass for those components. Low muzzle velocity reduces recoil impulse compared with a high-velocity anti-tank gun. The cost is a weapon that behaves more like a large mortar or low-pressure cannon than like a standard direct-fire gun. It produces a higher trajectory, a slower time of flight, and a stronger dependence on correct range estimation. The firing system is percussion-initiated. The projectile is loaded, and the propellant cartridge is secured to the base of the round. This simplifies supply and reduces crew errors with separate charges. Ignition drives the projectile through the smooth bore at relatively low velocity. Without rifling, spin stabilization is not used. Stability depends on projectile design and consistent manufacture. The system has little tolerance for defective ammunition components, because the crew is close and the mounting does not isolate them from blast effects. Two principal ammunition natures are associated with the weapon. One is a high-explosive shell for anti-personnel use, commonly described at about 8 pounds. The other is an anti-tank bomb, commonly described around 6 pounds. The anti-tank effect is achieved by a shape charge principle rather than kinetic penetration. When functioning as designed, short-range penetration figures around 60 mm are cited in technical summaries. This does not convert the weapon into a general anti-tank gun. It confines its practical use to short range, favourable angles, and prepared firing positions. Range reporting varies because it mixes ammunition types and different trial standards. But with the high explosive shell, maximum range is commonly noted at about 500 yards. With the anti-tank bomb, maximum range is often given at about 200 yards. Longer figures appear in some trial notes under ideal conditions, including claims on the order of 1,600 yards. Those longer distances do not represent practical employment because aiming, fuse reliability, and mounting stability limit effective use well inside the theoretical maximum. Sighting arrangements are minimal. The intended units do not have time for full gunnery instruction. Some detachments improvise reference marks on the shield or use local aiming stakes. That produces variability between units. Traverse is theoretically full circle, but fine adjustment depends on how the crew can shift and control the weapon on its wheelbase. Their elevation is limited but sufficient for lobbed fire, with maximum elevation commonly stated around 40 degrees. The elevation mechanism itself is simple, but stable elevation depends on the base seating and the crew's ability to keep the mount from rocking. The logistic package includes a trailer and limited on-gun stowage. Technical descriptions note that up to 10 rounds can be carried on the gun, with additional rounds carried on the trailer, often around 40. This matters because local defense detachments cannot rely on rapid resupply during an alert. It also creates a handling burden. Each round is heavy. Each round must be stored and moved without damaging the fuse and without deforming the cartridge attachment at the base. Simplifying choices create predictable failure modes. Handling injuries are the first category. Tipping a 600-pound assembly onto a wheel requires coordination, leverage, and stable footing. Wet grass, loose gravel, rubble, and road cambers reduce control. An uncontrolled fall can crush hands, legs, or feet. The weapon can also pin a crewman against a wall or bank during positioning. In urban areas, maneuvering space is limited, and the recommended use of ropes for movement is an administrative admission that the carriage is not suited to narrow streets and tight corners. Positional instability is the second category. The base wheel spreads load like a plate, but it is still a wheel, not a spade. On soft ground, it can settle unevenly. On hard ground with uneven surfaces, it can rock. If fired without stable seating, the assembly can shift between rounds, degrading aim and raising the risk of the weapon tipping. Crews tend to reset after each shot, but that consumes time and requires additional handling, increasing the chance of injury. Ammunition malfunction is the third category and the most serious. The Smith gun's credibility depends on fuse reliability and safe explosive behavior in storage and handling. Early batches of ammunition are reported to have faulty fuses, including premature explosions during live firing. A fatal incident during a live-fire exercise in 1942 results in the death of Corporal Cecil Edward Maynard of 2819 Squadron, RAF Regiment. Subsequent concerns lead to withdrawals from some units, and by 1943 the weapon is removed from RAF Regiment service. Ammunition scarcity amplifies these risks. Many detachments are supplied with only a small number of anti-tank rounds per gun, sometimes described as 6 or 7. Though this quantity does not support extensive practice, it also reduces confidence. A crew that has fired only a few rounds cannot develop consistent loading habits, correct tipping drills, and correct safety spacing. Headquarters attempts to compensate with printed instructions and mandatory procedures. The procedure can be correct on paper while remaining ineffective in practice when the limiting factor is time on the range. Testing exposes the gap between prepared demonstrations and local conditions. In trials on flat ground, the gun can be tipped into firing position, aimed and fired with predictable results. Under those conditions, penetration can be shown against plate and range can be recorded. In local service, the weapon is stored in sheds, moved over uneven ground, and operated by crews that may change week to week. Ammunition may have variable storage conditions. Tyres may deteriorate. Small defects then translate into major practical limitations. Deployment is structured around static defense rather than maneuver. Positions are selected in advance. Units prepare level pads or shallow emplacements. Weapons are assigned to cover choke points, bridges, road bends, and likely tank approaches. Some are positioned to cover airfield gates and perimeter roads. The full-circle traverse is less valuable in this context than the ability to put a projectile into a narrow approach line from a position that can be held by a small crew. Training is reduced to a small sequence of actions. Move the weapon onto the pad. Tip it onto the base wheel under control. Confirm the base is seated and the assembly is stable. Load the projectile and confirm the cartridge attachment and seating. Clear the crew to positions that reduce exposure to blast and fragments. Fire using percussion. Observe impact. Reseat the weapon if it has moved. The steps most likely to fail are those that depend on ground and coordination, not those that depend on technical judgment. Transport practice adds an additional problem. Some units discover that the piece can be towed behind civilian vehicles because the wheel arrangement will roll and the weight is within the capacity of small lorries. Official guidance discourages towing at speed because wheel and axle damage can follow, and the weapon is not engineered for sustained road transit. The result is a typical local defense compromise. Units want to cover multiple points. The supply system wants to prevent a maintenance burden on a weapon already built with narrow durability margins. Operational outcomes are defined by exercises, guarding duties, and readiness drills. The weapon is not fired in combat against German armour because no invasion occurs. That absence does not remove operational relevance. It shifts evaluation to whether the system would likely function under stress, and whether it changed local defensive planning. Some reports describe the gun as awkward, heavy, and dangerous. Other units report that when emplaced and properly handled, it provides credible short-range firepower for its intended role. Institutional impact is visible in paperwork rather than narrow years. A weapon that causes accidents produces reluctance to handle it. That reluctance shows up as limited live fire sessions, avoidance of tipping drills, and the request for alternative equipment. Command responses take the form of memoranda emphasizing correct drill, strict storage, and safe handling. The language is procedural. It treats mishaps as correctable errors and treats reputation as a training issue. The same pattern appears in Soviet rear area reporting on some emergency anti-tank measures, where simple devices create avoidance behavior if safety incidents occur during short training cycles. Enemy response is minimal. The Smith gun does not generate battlefield intelligence reports because it does not see combat use. German forces do not require a dedicated countermeasure for a weapon that remains in Britain. The relevant strategic response is internal and comparative. As British production improves, the more effective anti-tank systems become available for local defence, including the Piat for infantry use and increased availability of standard anti-tank guns such as the 6-pounder. In the Soviet case, the equivalent shift is toward more reliable distribution of standard anti-tank guns and improved infantry anti-armour doctrine as production and training stabilise. The Smith gun's strategic role is therefore temporary and administrative. It fills a perceived capability gap during a period of acute invasion fear and limited conventional gun stocks. It provides a tangible item that can be issued, counted, and assigned to a map reference. That has value in reporting. It allows headquarters to state that a locality has an anti-tank capability, even if the capability is constrained by range, ammunition, and handling risk. And it also consumes industrial effort that later appears less efficient once standard weapons become available again. By 1943 and 1944, the threat environment changes, the invasion danger recedes, Home Guard roles become less central, standard weapons distribution improves. Ammunition priorities favour standard calibers and systems used overseas. In that environment, the Smith gun becomes an anomaly in inventory. It remains present, but incentives to improve ammunition, expand training, and refine safety components decline. Risk management also pushes it out of higher oversight environments, which is consistent with its removal from RAF regiment use after accidents. Post-war evaluation treats the weapon as a product of the industrial improvisation, and it is catalogued as an expedient smooth-bore anti-tank piece with unconventional mounting and limited effective range. The record highlights the mismatch between intended ease of manufacture and real handling complexity. It also notes that ammunition scarcity prevented adequate practice, reducing both safety and effectiveness. The weapon is declared obsolete in 1945. Replacement is not a single successor. It is the restoration of standard anti-tank guns in garrison stocks, combined with infantry anti-tank weapons that can be issued without a specialized carriage system. The remaining examples in collections show what the device was. It looks ordinary as a gun on wheels. The risk is not in a complex mechanism. It is in a low-margin design, an awkward mount that demands stable ground, and ammunition that must function correctly despite being produced and stored under wartime constraints. This weapon was a technical decision born from wartime pressure, effective on paper, limited in the field.